so I suppose everyone should be able to hear me. Yeah, my name is Rico Friedrich. I'm also a postdoc in the AFLOW group, and I will today, let me share the screen, speak about primarily polar materials. So, yeah, so I guess you should be able to see the presentation now. Okay, so about polar materials and the tool that we have developed, the associated tool is the AFLOW-CCE. So this is a rather new development still in AFLOW. So we've been implementing this within the last months and releasing it also. And polar materials are in a sense fundamentally different than what Corey just showed before with the alloys. And I will try to spend a decent amount also in some theoretical background, because the final tool is very easy to use. Is very simple actually to correct the DFT formation energies and the results. But there's many physics and many properties went into this, and I would like to tell you about this, why we believe this is such an achievement to have something like that. So at first, as a motivation for polar materials, I want to start out with the periodic table. And when we, let's say, highlight first the elements that are metals, that of course covers by far the largest part of the periodic table. So all these elements in blue are metals. And when you form compounds between these, you get alloys, what Corey just showed. So the convex hulls that Corey was referring to were mostly compounds of these elements. And what you could also see was, for instance, for this palladium-platinum hulls, for the system out of these two elements, actually the hull is not very deep. It is relatively shallow, at only a few 10 or maximally 200 milliev per atom deep. However, when you now form compounds of, let's say, these elements with low electronegativity, so with the metals, with the other corner of the periodic table, so as elements, they are non-metals, they have a very high electronegativity, usually like oxygen, fluorine. And this is what is meant by polar materials, that you have a combination of a low electronegativity element and a high electronegativity element. And so the bonds inside your material are very polarized. The electron density is very polarized towards the element with the high electronegativity. Well, of course, if you would form a compound of silicon and oxygen, since oxygen has such a high electronegativity, it would still be very polar. But mostly you form those polar materials as a combination of, let's say, the green ones and the blue ones we saw before. And this is actually a much bigger problem, because these alloy systems, they are very well described within plane density functional theory. So that is not a big problem. So there you can just use your basic theory and it works out. But these polar materials are much more complicated. And maybe first, as a motivation, that they are really important, I give you some examples where polar materials play a very critical role. So when you look, for instance, the battery materials, so for instance, you have this lithium iron phosphate material. So this is an oxide, it's a very polar compound, and for energy storage purposes, it's very important. Also for all kinds of transparent conductive, so for displays, these transparent conductive oxides are very important. And also as coatings for all these cutting tools, and also in aerospace technology, you want to have very thermally resistant materials, potentially ceramics, and these are of course polar materials. And we want to be able to study and design those materials with AFLOW, with our software. And as I indicated already, this is quite a challenge. And why is that? So as an overview, I will first speak about the physical foundations of formation enthalpies a little bit more. Also, the finite temperature contribution, let's say, so a vibrational contribution that leads to thermal effects. Because we usually do the calculation at DFT at 0 Kelvin, but of course the measured values and where you usually consider these materials are at room temperature. And then I will explain this coordination corrected enthalpies method. This is what CCE stands for. We will see an application to ternary oxides and halides. And they can also correct the relative stability of polymorphs. So this is the only scheme that can actually do this. And then there's a AFLOW-CCE command line interface and the web app. And we will use these actually only the command line interface during the exercises. So we can use this for oxidation number determination and of course for our corrections for the formation enthalpies. So let's start out. Let's consider a bit more closely what this formation enthalpy is. Corey outlined it already. So when you have a formation enthalpy of a compound, AX1, BX2, it is the enthalpy of your compound minus the stoichiometrically weighted sum of the enthalpies of your so-called reference phases, elemental reference phases. Yeah, that's what I just said. And then you, for ionic or polar materials, look to the most common group, the most common materials class, so for instance, oxides. When you look at the chemical nature of these materials and the reference phase, you will find that the compound phase is typically an ionic insulator. So with a very large band gap and chemically very inert and all these kinds of things. However, when you look at the elemental reference phases, so let's say you have magnesium oxide, so magnesium oxide itself is an insulator, but the elemental magnesium reference phase would be a metal. So you have the band stick cross your Fermi energy, so this blue line. And the other reference phase would be elemental oxygen. So an oxygen molecule, where you even need to consider that the oxygen molecule is the ground state is triplet oxygen, so it is spin polarized. And that means you have chemically very, very different systems. You have an insulator, you have a metal, and you have a molecule. And this is a very big complication for density functional theory, because density functional theory usually lives from an error cancellation, effects between when it calculates energy differences between chemically similar systems. But when they are not chemically similar, it cannot get this error cancellation. And we can visualize this maybe even a little bit nicer, that for these compounds, when you have transition metal oxides, the densities for those states, the electronic densities are very localized around the transition metal centers. So you get very strong electron localization effects where DFT usually has a problem. And for the metallic reference phase, you basically have this Fermi sea of electrons around those nuclei, so very extended. So this is something very different. And to outline actually even a little bit better that you have a problem here, I came up with this explanation that we have certain constraints when we want to do autonomous computational materials design. So we can think of this as some boundary conditions that we want to have fulfilled, and these are 3 boundary conditions. So I wrote them at the corners of a triangle. So you want to do high throughput materials discovery. So we want to do this for thousands or millions of materials. This is one condition that we have. And ideally, you want to do this also ab initio, so without empirical parameters. So like ab initio DFT. So this is our ideal, because then usually the theory is very universal and you can apply it to all kinds of materials. And of course, we want to be accurate. And when you have metal alloys, so what Corey was speaking about, when you use standard DFT, so standard semi-local DFT, within these some sort of standard functionals that are used, this is good enough. So I can write this into the middle of my triangle, meaning that all these 3 conditions that I put at the corners are fulfilled. However, when I go to polar materials, and I have the same triangle, I have the same conditions, the question is, what would be such a theory that fulfills all these criteria? And now, after thinking quite a long time about this, I think the answer to this is that there is no such theory. Because as I will explain right now, you cannot fulfill all these 3 criteria for these polar materials. Because when we look at semi-local DFT that before did the job, it is still high throughput compatible, and it is still ab initio, of course, but it is not accurate, as we will see. So, and of course, we don't want to compromise on accuracy. But if you go to that edge of the triangle, so we want to have a theory that gets it right. So we want to be ab initio and accurate, but we don't care about the computational cost. We are able to lift this high throughput compatibility. Even there, we do not really know how such a theory would look like. People have spent a lot of computation time on very expensive methods, and it was still not accurate enough. So what we actually need to do, and this is what the CCE method does, is we need to lift this ab initio condition a little bit and say, okay, then when we correct our DFT results empirically, we are high throughput compatible, and we are accurate. And this is actually what we want to do, so then we can do materials design. Yeah, so let's look a little bit more closely into what we actually calculate and what is measured experimentally. And of course, this is our ballpark to what we need to compare. So what we directly get from density functional theory is what is called the formation energy. So the energy of in this example, a binary oxide, minus the energies from DFT for the reference phases, or let's say the metallic reference phase and the O2 molecule. So this is what I get from DFT immediately at 0 temperature and pressure. However, what is measured experimentally is the formation enthalpy at room temperature. So the enthalpy of the compound minus the enthalpy of the reference phase at this reference temperature. So now we can say, okay, our enthalpy is the energy plus this PV term. So there's just a definition. And we can insert that into our equation. So we replace each of these H's by E plus PV. So this is the energy of the compound plus the PV term of the compound at this reference temperature. And now we can make a first very accurate approximation, actually, that we can cross out these PV terms for the condensed phases. So for the compound and let's say for the metallic reference phase. Because this is so small that you can neglect this. However, you cannot neglect this PV term for the O2 molecule. And then what you do then is, since you have all these energy terms at the reference temperature, you write this as the energy at 0 Kelvin plus the energy difference between 0 Kelvin and room temperature. And also for your reference phases, and as I said, the PV term at room temperature for the O2 molecule has to stay, because that is not so small. And then when you do this, you can identify your energies at 0 Kelvin with what you usually calculate in DFT. So this you calculate in a certain approximation from DFT. And those energy differences between 0 Kelvin and room temperature, we can calculate with what Cormac will be speaking about tomorrow with the HEL module, so the vibrational properties, because the vibrations, this is what is usually excited at finite temperature. And then, of course, for our O2 molecule, we also need to make some estimates. And this is very simple physics, because we have a diatomic gas, and with 5 degrees of freedom, 3 translational, 2 rotational, the vibration of oxygen is not excited at room temperature. So it is 5 halves kBt for a perfect diatomic gas. And the PV term is, according to the ideal gas law, another times kBt. And when we sum that up, we get 90 millieV per O2 molecule. And this is exactly the same value as you find it in reference books. So what we can then sum this up with is that within a very good approximation, the measured experimental result at room temperature is what you directly get from DFT within a certain approximation, of course, plus the vibrational term where all these temperature effects go in. I should maybe say that also 0-point vibrational effects should be included, and we also included them, but for clarity, I omitted them. So this vibrational term here stands basically for finite temperature effects. So we can express this now like this. And we can now, since we can now calculate both these terms, we can look what actually gives us the big errors. Is it this term, the green term, or is it the blue term that comes from the finite temperature effect? And this is what I did for 71 ternary oxides. And you can see here, I mean, they are listed on the bottom and top. And in this lower panel that is, that is around this, that's red bars around, you can see that this is this vibrational contribution. And this is very small, because it's maximally something like 20 millieV per atom. And so it's not completely negligible, but it is very small. So this is not the term that gives us the errors. The term that gives us the errors is from the DFT. So here's the actual difference between the calculate and the experimental formation enthalpies. So this is the error, and the 0 line would indicate perfect agreement. However, most of our points are far away from this 0 line for 3 different flavors of density functional theory. So no matter which one of those 3 I take, I don't get good results. And the best measure for this is maybe the mean absolute error. And you see that the mean absolute error is in all cases larger than 100 millieV per atom. And when we think of the fact that room temperature is 25 millieV per atom, so we are our error is a factor of 4 at least bigger than room temperature. So we cannot make materials discovery and design based on this because we are simply not accurate enough. So we need to work on this. So yeah, that's just outline, and this will be also the test set for our scheme, for the CCE scheme. And what I hopefully could convince you with is that this term that we approximate from DFT, the formation energy part, this is what gives us the large errors, and the vibration term is not that important. We can calculate it actually very reliably, but it's not that big, so we can kind of grade it out. And now let's come to how we actually correct these formation enthalpies. And this came about when I looked at these systems in this way. That I said, okay, when we have calcium oxide, then we have 6 calcium oxygen bonds. So the calcium is 6-fold coordinated octahedrally by the oxygen. When I go to the rutile phase of TiO2, my titanium is also 6-fold coordinated by oxygen, so there are 6 titanium oxygen bonds. However, when I react those two to form perovskite, like the prototypical oxide, what I get is this structure. And there I have 6 titanium oxygen bonds still, but 8 calcium oxygen bonds. So the coordination number has changed. And since the number of bonds is maybe the most fundamental property in chemistry that determines the stability of a system, I thought this is the key to the problem that you actually should correct with respect to the number of bonds that you have. So here you have these 8 bonds highlighted. And so this is what we do. We do a correction based on the coordination, therefore coordination corrected enthalpies, so on a proper basis. So we take our calculated values for the binary systems, this is our fit set, subtract from that the experimental values, the best experimental values that we can find, and then we assign them to these corrections per bond that depend on the cation and the oxygen and also the oxidation number. And then when we have that from our fit set, then we can apply these to calculate coordination corrected enthalpies in the sense that we have this, again, the calculated one for the ternaries, because ternaries are our test set. And then we subtract in this way these corrections by taking care of these corrections per bond. And I have deduced these corrections for many systems or for many oxides already in several oxidation states. So in this publication, there's actually a big table where for 3 different functionals, PBE, LDA, and SCAN, we have all these corrections listed for all the different oxidation states. And this oxidation state dependence is also very important, because when you look at vanadium, for instance, vanadium is known to be to occur in oxidation states +2, +3, +4, and +5. And when you look at the corrections, they are also very different. So there's actually a nice trend, but they are very different on a per bond basis by more than 100 milli-eV per atom. And I go from +2 to +3. So this oxidation state dependence is also a very important criterion for this correction. And then there's the reason why I actually told you so much about this vibrational part, about the thermal contribution, because we can now include all these thermal effects in our corrections. So what we do for room temperature is we take the experimental room temperature formation enthalpies that we get, then we fit our corrections to our calculated DFT formation energies for our fit set, and then we have one set of corrections for room temperature, meaning that when we apply these corrections to pre-calculated DFT formation energies, we get a direct estimate of the room temperature formation enthalpy. And now for 0 Kelvin, we can do a little trick, because we start again from these experimental room temperature formation enthalpies. And since we can calculate those thermal properties for our fit set, we can subtract the thermal contribution from these experimental formation enthalpies. And then we get a good estimate for the 0 Kelvin formation enthalpy. And then we can again fit our corrections to the DFT values with respect to these estimated 0 Kelvin formation enthalpies. And then we get a second set of corrections that when you apply them, we get a direct estimate for the 0 Kelvin formation enthalpy. So that means you don't need to worry about this thermal effects, because we have 2 sets of corrections. So all these effects are included in the corrections, and our tool gives us actually an estimate for the room temperature and for the 0K information enthalpy. This is, I think, pretty nice. So of course, how good does that now actually work? And the first thing to consider in this regard, or the first example, is this, this prototype example with the perovskite. So what we do here, so for all three functionals, PBE, LDA, and SCAN, so all three flavors of DFT, I show the deviation of our predicted result with respect to the experimental formation enthalpy, and for our CCE method, the correlation correct enthalpies method, and another method that has been around before, the quasi-Ferro method. So Ferro stands for fitted elemental phase reference energies. And you can see that in every case, we are significantly better than this previous method. And that even for SCAN and LDA, we get an error bar that is, with respect to experiment, that is very, very small, and much better you will actually not be able to get, because there is also in the experimental values, there's some measurement uncertainty, and so that will ultimately limit your accuracy. But of course, I can show you that this now as well for the whole set, for this whole material set of 71 ternary oxides. And I show you this based on the SCAN results, based on the results for the SCAN functional, because this is usually the most accurate functional. And there we can also see that our black dots, this is our method, and the gray dots is the previous method, quasi-Ferro, and this is again the error between our corrected results and the experimental result. And this dashed line would indicate perfect agreement, and these red lines are at plus minus 50 millieV per atom. And previous methods have achieved this accuracy, and when we have all dots inside these red lines, what is the mean accuracy of the other methods, then that means we are significantly better. And with these black dots, we actually pretty much get that. We have all the black dots inside red lines, and our mean absolute error here for the CCE is at 27 millieV per atom. So now very close to the room temperature thermal energy, what we of course need and must have to materials design. The quasi-Ferro method is 44, so we are significantly better on a quantitative level with our method. And we can now even look at the outliers. So for instance, for this iron aluminum oxygen system, there we can see that both our CCE and the quasi-Ferro method, and we actually see this for all three functionals, have a rather big deviation from the experimental result. And this indicates, since these methods do something fundamentally different, that here the experimental result might be wrong. And something similar for this strontium-hafnium oxygen compound. So we are even able to pinpoint where maybe experiments and measurements should be redone, because we believe we are more accurate there. And then let's show also how general CCE is, because I have shown this only for oxides so far. And we have tested that also on ternary halides. So the point with ternaries is that besides oxides, there are not so many known ternary compounds of polar materials that are well characterized by thermochemical data, which you of course need to benchmark your results. But there are some ternary halides around, and you can see that plain DFT again gives you rather large errors. Of course, the set is so small you cannot really have a statistical significance here. But when you correct them, you get very nice results, and especially again with SCAN, you get them very, very close to the zero line, and actually even better in this case, I think, than the thermal energy at room temperature. Now we are here at 24 millieV per atom mean average error, or mean absolute error. And then this is what I also mentioned before, that our method can do something what other methods cannot do, because DFT sometimes predicts the wrong structural ground state for certain systems. So it just gives you the wrong polymorph, as we say, to be too low in energy compared to what the experiment would give you. And one example that this is known is this aluminum silicon oxygen system. So there, the so-called kyanide structure is the experimental ground state. However, PBE finds what is called andesite as the ground state. And this is visualized here. So the zero line, the zero line is the energy of the experimental ground state. So any dot that we get below the zero line yeah, must be wrong, because that would be erroneously more stable than the experimental value. And PBE does just that. So it gives this green dot below this line. However, when we apply the CCE method, so we get then this blue dot, then you shift it up slightly above this zero line. So we correct the stability in this case. And we see something similar for actually much more complicated systems. For cobalt oxide and manganese oxide, they are also, let's look at the cobalt oxide case. They are plain PBE and plain scan predict the wrong ground state structure. However, when we correct this, we shift both above the zero line, so we retain the correct relative stability. And this is a very nice feature, I think, of our approach, that we can actually do this. Yes, and that brings me now to this command line, to the command line tool that we have been implementing. So yeah, of course, feel free to ask any kinds of questions that might come up. But then I will actually try to show this maybe over the portal. Let me see if I can move this over. So, yes, maybe I can zoom in even a little bit more. So here we are in this AFLOW day 2 directory, and you can now see all these directories, and we go now to this 062 CCE1. And there are a bunch of structures, and we will do the exercises of them soon. But what you can do first with the CCE I want to show is you can just type AFLOW --CCE. It's a very simple command, and what that does, it gives you user instructions. So you could go through this actually by yourself, and it tells you how to use it, but it also provides an example structure down here for the magnesium oxide system. So I just want to highlight this case. So I copied this structure now, and what I can do now, let's say I make a file post-star, and then I click insert, and then I can paste this this structure into the editor, and then I just save it. And now I can show the basic functionality of the CCE, and you could maybe follow along either on the slides, or let me see whether the PDF gives us actually the maybe the better view. Yeah, I mean, it's kind of small. I can try to reduce the width of this a little bit more, just to see. Because what I want to do now is I want to correct the results for this structure. And what you would just do is you type AFLOW --CCE equals, and then this postcard, you can use step completion here, MGO. It will be just saved. Well, I just saved. And when you do that, yeah, okay, there are some longer lines. And what you can see, so this is the command that I just typed. And what this CCE algorithm now does, it analyzes the structure and analyzes the number of bonds, cation-anion bonds in the structure, because this method is based on this. And it also, as I indicated, depends on the oxidation numbers. So it has an algorithm to determine the oxidation numbers in your system. So by just putting this structure, you get those oxidation numbers. It correctly finds that magnesium is +2 and oxygen is -2. The algorithm that I have implemented, I do not have yet found any system for which it doesn't work, but I still put here that you, of course, should check whether it gives you the correct results, but it will check whether the sum of your oxidation numbers is 0. And this is, of course, the important criteria. But it works very nicely. It's based on Allen electronegativities. So we will actually do an exercise where we see that you can use this functionality. Even if you're not interested in the corrections itself, you can use it to determine the oxidation numbers in your system. And then you get the actual CCE corrections, and you see that they are printed per cell and per atom, and for these two temperatures. So for room temperature and for zero Kelvin. And this is what I just said. You need just to provide the structure, and you immediately get corrections for room temperature and for zero Kelvin. And you have this for three different functionals, for LDA and for scan. And then there is something that I highlighted here. This is called CCE at experiment. And maybe at this I need to explain a little bit better in the sense that I put the presentation on. Because when we do the CCE on top of normal DFT, on top of scan, let's say we get very nice results. But of course, since we do this per bond, we could also say, okay, we can maybe break down our experimental values to values per bond on a per bond basis. And these are these blue dots. So without doing any DFT calculation, we can get a rough guess of the formation enthalpy of the system. And this guess is actually remarkably accurate. It is 244 milliliter per atom, mean absolute error. So it's, of course, much less accurate than if you actually do it in DFT. But without doing a DFT calculation, to have already such kind of results is also maybe already pretty useful. So this I wanted to highlight. And then we can move on. So with this functionality, I've just seen you can now also type minus functionals and just select the functional that you want. For instance, you want to only have the result for the PBE. So then this gives you only the CCE corrections for the PBE functional. And then you can also provide your pre-calculated DFT formation energies. So what you do is you just add minus DFT formation energies equals, and then as a comma separate list, you give it your pre-calculated formation energies. And this is for magnesium oxide minus 5.434 EV for PBE, then minus 6.220 for LDA, and minus 6.249, if I'm not mistaken, for scan. Yeah. And then, of course, you need to specify to which functionals these formation energies belong. So in the same sequence, you need to write now in your functionals tab that this is for PBE, for LDA, and for scan. And when you do this, when you hit enter, then you get immediately the corrected values. They all agree perfectly in this case because magnesium oxide was used to fit these corrections, and our scheme is set up such that it reproduces the results to which it is fitted exactly. And so therefore this minus 6.235 EV per cell at room temperature is the exact experimental value that we used to obtain these corrections. This is something you can do. And then there's also the functionality. Let's say, let's use this command. You can say oxidation numbers equals, and as a comma separate list, you can give it the oxidation numbers for all the atoms in your system. As I said, they are automatically determined, but if you desire so that you want to provide them by yourself, you can do that. But as I said, I have not yet found a system that the ultimate determination does not work, and then it would give you actually that you have these input oxidation numbers that you provided them, and it gives you, of course, the same result. So this is it up to this point, and then, yeah, maybe I just switch on the presentation for one more second. We have also now developed, especially in collaboration with Max Brenner, an online interface, so that is available via AFLOW online. So when you go there, then you already see that there is a coordination corrected enthalpies field, so you can provide a structure. You have actually to activate the CCE methodology, and you can provide a structure file, in this case the postcard, again for the magnesium oxide. Then you can say for which functions you want to have the corrections, and you could, as an optional tag, also provide oxidation numbers. And this is available there, and this is what we will also develop a little bit further. And yeah, I should highlight that in the end you need to hit submit, but we also had some exercises on the AFLOW online, so I think you already know this. And then we want to do some, I think, very simple exercises with the CCE functionality inside the breakout groups. So the first one addresses the functionality of the CCE to give you oxidation numbers. So I think this is useful on its own. And in this case, I want you to determine with the CCE the oxidation numbers of this lead molybdenum oxide. Because there could be some ambiguity of what the oxidation numbers are. And therefore you should also think, what would I expect, what oxidation numbers I get. And then you should take a look at the CCE corrections for the magnesium tungsten oxide at room temperature, and take a look for which function is there the largest correction. And the main purpose of this is to see that these corrections are very, very large, which means that the DFT errors are very, very large. So these corrections are very significant in this sense. And then we do another exercise with this functionality to provide pre-calculated formation energies from DFT. So I give you here these pre-calculated formation energies. I should say that they are per cell. You need to provide them on a per cell basis and with the corresponding functionals for this perovskite structure. And you can see what the corrected values are. And yeah, how this basically works. And how well also the corrected values there coincide. This you can basically discuss inside the groups. Okay, then I guess we just sum this up very quickly. So then I just share my screen very briefly again. So yeah, these exercises are basically there to indicate a few different features. So if you do the AFLOW -CCE for the score, you can actually use the tab right here for the lead molybdenum system. You see that it gives you for molybdenum +6 and for lead +2. And this is in a sense, yeah, important or interesting because they could also be both +4, because considering where they are in the periodic table, molybdenum can be +4 or +6 and lead can be +2 or +4. However, due to the fact that the molybdenum has the lower electronegativity, it should occur in the higher oxidation state. And this is what the algorithm does correctly, and therefore these assignments are correct. And this is also my experience that these island electronegativities that we are using are very well suited to get these oxidation numbers right. And then you, of course, get also the output for the CCE, but the main focus was here on the oxidation numbers. So you can also use this for other things. Then the CCE on the postcard for magnesium. For the magnesium one, and then you can take a look how large these corrections are actually, and you see that they are all very large. They are all several hundreds of millieV per atom, and that the one for the LDA, room temperature and 0 Kelvin is the largest one. So these corrections are very, very significant. You cannot be reliable without those, and actually for all three functionals. And then of course the last one would be most tedious example in a sense. We have this postcard for the perovskite -DFT formation energies, and then you really have to insert those -63.452, -72.084, and -72.412, and then you have to give it the functionals. PDE, scan, and hopefully I don't have a typo. No, it looks good. And then you get the correct values down here, and they all, when you do it on a per atom basis, let's say for the 0 Kelvin value, because we're looking at the 0 Kelvin value here, they agree very well. So the deviation between the different correctors values is maximally something like 30 millieV per atom, and LDA and scan are even closer. So that shows that these corrections are also very consistent among each other. Yeah, this is pretty much the points I wanted to make. You actually have the solutions also on the slides because I decided to put them there. So these answers and also the commands. And yeah, I think this is pretty much it.